Welcome to The Explainer. So, what if I told you we could tell the entire story of a journey? I'm talking every start, every stop, every dramatic pass, without using a single word. It sounds kind of impossible, right? Well, today we're going to unlock the visual language of motion and show you exactly how it's done. Just think about it. If you were trying to describe a race between two people, you'd have to explain who started where, who was pulling ahead, who was faster, and exactly when one person overtook the other. It's a lot of words.
Yeah, trying to do all that without words, it really does sound impossible. But physics has this incredibly elegant way of doing it. It can capture that entire story in just a single silent picture.
That's what we're going to do today. We're going to learn how to read these visual stories, how to transform one simple line on a page into a whole dynamic journey. Okay, let's dive right in.
All right, so before we can start drawing the story, we've got to learn its language. And just like any language, you have to start with the basics, right? The core vocabulary. In this case, the vocabulary of motion.
Okay, first things first. To keep it simple, physicists have this little trick. They imagine any moving object, doesn't matter if it's a huge planet or a tiny car, as just a single dot, a material point. This way, we can just focus on the journey itself, We don't have to get bogged down with its size or shape.
And the path that this little point follows, that's what we call its trajectory. It's basically the invisible line it draws through space as it moves. Think about the beautiful arc a basketball makes on its way to the hoop, or the perfectly straight line a sprinter runs. That's a trajectory.
Now, how do we talk about how fast it's moving along that path? Well, that's where velocity comes in. And for now, let's just focus on average velocity. This isn't your speed at any one moment, like looking at your speedometer. It's more like the overall pace of your whole road trip, from the moment you left your driveway to the moment you arrived.
And figuring it out is actually super straightforward. There are just 3 steps. Step 1, you measure the total distance covered, the displacement. Step 2, you measure how much time the whole trip took. And step 3, you just divide that distance by the time. Boom. That's your average velocity.
Okay, so we've got our vocabulary down, we have our point, our trajectory, and our velocity. Now let's put it all together and actually draw the story. This is where the magic really happens, and it's all thanks to something called the space-time graph.
So a good place to start is just by, jotting down some data. We can make a simple table like this one. You see? At time 0, our object is at position 0, the starting line. 1 second later, bam, it's at 10 meters. 2 seconds in, 20 meters. You get the idea. But let's be honest. A table of numbers is kind of boring and hard to read quickly. The real magic happens when we take those numbers and plot them on a graph. We put time along the bottom and position, or space, going up the side. Then we just connect the dots, and suddenly, it's not just data anymore. It's a visual story.
And that line, that's our space-time graph. That line is the story. But what is it actually telling us? What's the secret? Well, the key to understanding the language of this story is all in its shape, specifically how steep it is.
Okay, let's start with the absolute simplest story you can tell. An object that's just moving in a perfectly straight line, at a perfectly steady speed. No drama, no speeding up, no slowing down, just cruising along.
Now, physicists have a fancy name for this, of course. They call it uniform rectilinear motion. It sounds complicated, but it's not. Rectilinear just means it's moving in a straight line. And uniform just means the speed is totally constant. That's it.
And here's the answer to our question. Check this out. The steepness of the line, what a math teacher would call the slope, that is the velocity. So look at the graph on the left. That gentle slope, that's a slower speed. Now look at the one on the right. That super steep line, that's a much higher speed. It's that simple. Steeper equals faster.
Okay, this is where it gets really fun, because once you know how to read one of these lines, you can start reading 2 or 3 and see how their stories all interact. We're talking about visualizing high-speed chases, dramatic passes, and complete standstills, all just by looking at some lines.
All right, let's picture it. A classic Surpasso. One car overtaking another. On our graph, you can see the car that starts out behind has a much steeper line, right? That means it's going faster.
Now, watch what happens. That steeper line is catching up, it's getting closer, and it crosses the line of the slower car.
And that right there, that's what makes these graphs so powerful. That single point where they cross, it tells us everything. It tells us the exact time and the exact place that the pass happened. The whole story of that chase is captured in that one tiny intersection point. How cool is that?
Okay, next scenario. What about a stop, a fermata? Let's say our object is moving right along, and then bam, it slams on the brakes and comes to a dead stop. What does that look like on our graph?
Well, think about it. If you're not moving, your position isn't changing, right? But time keeps on ticking by. So, on our graph, a stop is just a perfectly flat horizontal line. The slope goes to 0, which means the speed goes to 0. No slope, no speed. Simple as that.
All right, last one. And this is the most dramatic move yet. The U-turn, the inversione di marcia. How on earth do we show an object that's moving away and then completely reverses course and starts heading back where it came from?
It's all about the direction of the slope. See that upward, positive slope? That means the object is moving away from the starting point. But when it turns around, the line starts to slope downwards. It becomes a negative slope. And that peak, the point where it changes from positive to negative, that is the exact moment it reversed direction. So, here's the big takeaway from all of this. A single graph, a few simple lines, can literally tell 1,000 different stories. This one tool, the space-time graph, is a crazy powerful language that lets us see everything, passes, stops, U-turns, without needing a single word of explanation.
So we've pretty much mastered the story of steady, constant motion, the world of straight lines. But let's be real. The real world is more complicated. Things speed up, they slow down, they accelerate. So what happens when the story gets complicated and the line on the graph is no longer straight? Well, that's a story for another time.